Okay. Shall we get started? Okay. Yeah, I guess I could talk more about this, but I'll just give you one more comment, because one of you asked a good question. Basically, how do you implement this? I think is important. You will read the paper, but as you can see, there's a lot that needs to go on to implement it. Basically, you need to really build these tables that give you Q values are really the reward values in the end. And you need to be able to index these tables. These are hardware tables. You're now really implementing how do you access a table with multiple different state attributes. Basically, these are number of writes and these are number of reads. As you can see, these are just two different state attributes. And on a given state with some number of writes and reads, you want to get a Q value, right? That's kind of like a two-dimensional axis. Of course, you hash the values and then you make it one-dimensional. But clearly, if you're very fine-grained in terms of your state, you may not generalize. If you're very coarse-grained, you may overgeneralize, right? So the way actually this is solved in hardware is by having multiple overlapping tables, partially overlapping tables, that gives you both coarse granularity and fine granularity at the same time. You'll read the paper for more detail, but you can see that if you have multiple overlapping coarse-grained tables, you get both fine granularity and coarse granularity at different parts. Okay. And this is the hardware design that actually enables you to query those tables. So you basically have some candidate commands based on the eligible commands, and you have some state attributes that you look at. You form these state action pairs, and you have some hardware that forms the indices to these tables, because these are really multi-dimensional tables, but you really want to form a single-dimensional index to get the Q values. Q values are the reward values. And then with these, you basically look at all of these arrays and then provide an estimate. This is for one of the state action pairs. I don't know what happened. It decided that the reward of this was not very high, apparently, so that decided not to show this. And then you basically pick the command that leads to the highest reward value with a max function. Of course, this is a pipeline for 2 wide, right? You're basically considering only 2 commands over here. And you can see that we broke it down into 5 stages in terms of pipeline based on our analyses. And this is how you do the indexing for the tables. So there's a lot of detail that needs to go on in terms of how you build this particular algorithm in hardware. Clearly, this is not a general algorithm, right? It's really specialized for the purpose of doing reinforcement learning in hardware for this particular purpose. It can be used for any reinforcement learning in the end, but we're using it in the memory scheduler. Okay. I guess there's nothing else that I want to show you since you're going to read the paper anyway. Any questions? Okay, now let's move on and talk about something different. Related but different. Related in the sense that this is also a memory problem, and it's going to make things even more complex. And whenever you add more variables to the problem, more goals, it becomes more complex, clearly. And we've seen this before, so I'm going to skip some of these parts. But I'll give you the fundamentals first. Basically, this is really about shared resource design. And shared resources are not just memory. We're going to focus on memory. And if you recall this picture, I had this nice, beautiful XFIG picture that I've been using for more than 10 years. I like it. I think it's nice because nothing has changed. Basically, if you look at this picture, most of the system is dedicated to storing and moving data. And it's also a shared resource, basically. You have all of these accelerators, cores, agents, whatever you call them. They're sharing most of main memory. And sharing is a very fundamental concept, right? We all share resources also, right? Instead of dedicating a particular resource to a hardware context or a person, allow multiple contexts or people to use it, right? Example resource in a node is functional units, pipeline, caches, buses, memory, interconnect, storage, right? Power also, actually, if you keep adding. So why do you want to do this? Because this improves utilization and efficiency. It improves throughput, right? Basically, when a resource is left idle by one thread or one context, another thread can use it. There's no, so basically, you take advantage of this fine-grained idleness of the resource. And there's no need to replicate shared data, clearly. It also improves cost because you don't really need to replicate the resources, right? It reduces communication latency. For example, if you have a multi-threaded processor, simultaneously multi-threaded processor, Intel calls this hyper-threading. I like simultaneous multi-threading better. But basically, if you have a simultaneously multi-threaded processor, you're executing multiple threads at the same time. They access the same cache. And if they're sharing data, you don't need to replicate the data, right? And that data is in the same cache, so you reduce the latency of access as opposed to going to a different cache. That's the idea. And it's also compatible with the shared memory model. If you're sharing a resource, and if you're sharing data at the same time, you have that piece of data not replicated. It's compatible with the shared communication. Okay, but of course, this doesn't only have advantages. Like everything else, it has disadvantages too, right? Resource sharing leads to contention for resources. And we see this in real life also, right? If you have a valuable shared resource, people fight wars for it, right, in the world. And we've seen this many times. That's something we haven't learned, for example. That's an example where human history, over the course of years, they have not learned, clearly. They have not reached this higher level space, which we were trying to reach with the memory controllers. We're really trying to reach this higher level space, right? It'd be nice if we reached that higher level space also in human history. But okay, resource sharing results in contention for resources. When the resource is not idle, another thread cannot use it, basically. You get this conflict. For example, if the space is occupied by one thread, another thread needs to reoccupy it because there's only one space. So as a result of this, sometimes resource sharing reduces each thread's performance or some threads' performance, or all threads' performance actually. For example, if you're doing A, B, A, B, A, B, and they're going to two different rows in the same bank, everybody's getting row conflicts, right? Whereas if the threads were running alone, nobody was getting row conflicts, right? So basically all of the threads' performance can reduce in this case. So overall system performance can reduce, and of course it's not the common case, but it could actually reduce. Okay, thread performance can be worse than when it's run alone, as I said. This also eliminates performance isolation. Basically, you get inconsistent performance across runs. When you run with thread X, you get some performance. When you run with thread Y, your performance goes down by 10x. It's possible because your performance is now dependent on what else the other thread is doing, because resources are being shared with that thread. This makes a lot of things harder, as we will see. Performance optimization becomes hard, for example. You optimize your program, you work very hard, and in the end, whatever you do is useless because some other thread is going to destroy all of your cache locality, right? That's why resource sharing could be really bad in those cases, right? Basically, thread performance depends on co-executing threads. And if you have uncontrolled sharing, free-for-all sharing, this degrades quality of service, clearly also a performance isolation as well. It causes unfairness and starvation, and we've discussed this. I've given you examples. I'm going to go through that relatively quickly. The memory performance attacks, for example, that we've seen was that. So basically, because resource sharing has a lot of advantages, we want to keep the advantages, but we want to eliminate the disadvantages as much as possible. We don't want to get rid of resource sharing. We want to somehow figure out how to efficiently and fairly utilize the shared resources while keeping performance isolation when we need it, and while having quality of service when we need it. Okay, so let me give you a very quick example. This is based on a relatively early paper that looks at cache sharing in multi-core processors. Basically, if this core is running one thread, thread 1, when it's run alone, it's using this much cache space. The other core is using this much cache space, but when they run together, this one may destroy the cache space of the other one. Why? This may actually be streaming and kicking out a lot of data. This is not the greatest example actually, but this is one example. The worst case example is this thread has a very small working set that fits the cache, and it has very good locality in that. This thread has a huge working set that overflows the cache, and it doesn't get any locality out of it. It keeps streaming, like 1 terabyte of data, let's say, whereas this one has 10 kilobytes of data. And when the resources are shared without any control, the locality of this thread can be destroyed, right? Because this is accessing 1 terabyte of data. And that's the downside of the problem with shared caches. Okay, so why is this so bad? I think I'm not going to make this, I'm going to make this very quick basically. Clearly this makes programmers' life difficult because an optimized program can get very low performance, and its performance varies widely depending on core runners. As a result, you put all of this effort into compilers, performance optimization, algorithm optimization, and in the end, you don't get much. Right? Because somebody else destroys your performance. This is completely out of your control, right? That's why you really need system support for this. It causes discomfort to the user, clearly, because an important program can starve. And this also happens. By the way, resource sharing is not a hardware problem only. It's also a software problem. In the software, you may have shared libraries. You may have shared locks. In fact, at some point, Microsoft had this not so great design. When you have Excel, Word, and some other Office application, they all went through the same storage library. And it turned out if one was waiting for storage, the other one got delayed, even though it had a much faster access. That's true for shared locks also, actually. They had some shared lock problems as well. I think they solved a lot of these. But basically, if you have bad resource sharing, unfair resource sharing in software, it could cause a lot of discomfort to the user also. But that's true for hardware as well. And it also makes system management difficult. For example, if you want to maximize the number of applications that are running on a system, and if you want to satisfy some service level agreement, how do you enforce that service level agreement when you don't control this hardware resource sharing, right? Basically, you can run 100 threads on a core, but you have no control over the hardware resource sharing, so you have no guarantees on how much performance you can guarantee to each thread. And this is exactly the situation right now. As a result, when people have very strong service level agreements, they don't consolidate. They basically leave a lot of the resources idle. That leads to huge energy efficiency problems, clearly. And you can imagine that I have a service level agreement with this thing, right? And if it doesn't satisfy my service level agreement, I'm going to drop it and I'm going to buy something else, right? So that happens everywhere. Service level agreements can be really negotiated with big actors or negotiated with the users also, right? And I don't like my how my service level agreements is satisfied by some of these things these days, especially when they get old. Okay, so basically sharing improves throughput. We get better utilization of space and bandwidth. Partitioning provides performance isolation, predictable performance. You get dedicated space. The key question is, can we get the benefits of both? And that's what the rest of this lecture is going to be about. And the idea is very simple, of course. At the high level, you design the shared resources such that they're efficiently utilized, controllable, and partitionable. And we're going to see multiple approaches to how to do this. And the hope is that you get no wasted resource, because clearly dedicated space leads to wasted resources, right? You could solve the problem with shared caches. You dedicate 1 megabyte cache for each core. And the core that's using 10 kilobytes is wasting 1 megabyte minus 10 kilobytes, right? And the core that's using 1 terabyte is not getting benefit from 1 megabyte anyway, to begin with. So there's a lot of wasted space. But we want also quality of service mechanisms for different threads. And we've already seen that memory system is the major shared resource. We're going to look at memory controller in this lecture, but a lot of the ideas are actually applicable to controllers over here and SSDs over here as well. Basically, threads requests interfere when threads actually inject requests over here. So I like thinking about this from this perspective also. Basically, you have these requesters that are injecting requests. How do you deal with those requests that are injected into the system, right? That gives you a different perspective, because maybe there should be other solution directions, right? Maybe you don't allow them to inject requests once in a while. That's another approach you can take, right? This is called source throttling, and we're going to see that later on. Today we're going to talk about memory scheduling, but source throttling is one approach also. You could use data mapping mechanisms. So maybe you have multiple of these resources over here. You map the data to separate locations so that you minimize the interference, right? Okay, so clearly this is going to be much more of a shared resource in the future. So let's talk about how we can do this. Basically, threads share the memory system, but memory system doesn't distinguish between threads requests. This is actually becoming much better. If I was giving this lecture in 2008, 2010 or so, this was true. Today, people are incorporating a lot of quality of service mechanisms. Caches are, for example, controllable today. Memory controllers are less so, but going forward, it's going to be much more, in my opinion. So most of the memory system, though, is free for all, shared based on demand. Control algorithms that you have are thread unaware and thread unfair, usually. Caches are fixed. Intel processors now have caches where you can provide quality of service with some mechanisms, clearly. But there can be more, clearly. Aggressive threads, if these control algorithms are unfair, then aggressive threads can deny service to others. And because these algorithms do not try to reduce or control inter-thread interference, right? And we've seen the impact of this. Clearly you remember this picture, right? How many people remember this picture? Okay, that's good. So I'm going to skip these. And you know that this was due to unfairness in the memory controller, and there are reasons for it, which we're going to not talk about now, and you know the memory scheduler is the reason. And you know that this could be a denial of service problem. Basically, this blue thread can deny service to the red thread because it's really exploiting some unfairness that's in the algorithm that's baked into the memory controller, right? So we're going to try to fix this. You've seen this slide also. And clearly this existed in real systems, as we discussed. Basically, these are real results from 2006 or so, you have the streaming application, random access application, and you get significant slowdowns on the random access application. That's true when your streaming application runs with GCC. That's true when the streaming application runs with some virtual machine also. And this becomes a bigger problem with more cores. Basically, you become vulnerable to denial of service. You become unable to enforce priorities or service level agreements, and you get low system performance. So why do you get low system performance also? Because some applications that are very heavy in terms of accessing the memory system, they basically get prioritized in the memory system. Whereas some other applications that once in a while send requests to the memory system, they get delayed. If you think about the oldest first policy, that's the impact of the oldest first policy, right? But these are the applications that can actually give you a lot of performance, right? Because they once in a while send requests to the memory system. If you prioritize them, they can utilize the cores much better, right? That's the idea. So you get much better core utilization. By prioritizing these extremely heavy applications, you're not gaining anything in terms of memory system performance because that application is very slow to begin with. So some of the memory scheduling techniques that I'm going to describe are going to take advantage of it. In fact, the Atlas mechanism that you're going to implement in your assignment is exactly going to take advantage of that insight, basically. Okay. So, but basically, if you don't handle it, so as a result, you get low system performance because these applications that are making very slow progress are being prioritized. These applications that could make very fast progress are getting delayed behind other applications in the memory system, so they get slowed down significantly. So, and in the end, you have a completely uncontrollable, unpredictable system. And you don't have performance isolation. Your performance depends very much on which application you're running with. So this actually becomes worse if the system scales. Let me give you one example over here. We haven't talked about interconnects, but if you really want to scale the system, you design a system that kind of looks like this, right? And people are implementing systems like this. Basically, this is a two-dimensional system. I think there are 64 cores over here. And let's assume that all of these are executing some applications, and let's assume that there's a memory controller over here, right? And let's assume that somehow you construct or by nature these applications are accessing this memory controller. They're really going through packet switch routers in this case. There are routers in each of these locations going through these links, and they're putting a lot of pressure, as you can see, on these links over here. And if you have very high bandwidth access to the memory controller over here, what will happen is some of these cores over here get denied service in the end. And this paper actually looks at that denial of service quite a bit. It shows that in some scenarios you get significant latency increases, like 5,000x, because this really depends on the scale of your system also. As your system scales, it becomes even worse. Clearly, this is very interesting because there are routing algorithms that could be another solution to this problem, but we're not going to talk about that until we talk about interconnects. So keep this in mind. This problem is not just the memory controller, it's really broader than that. And if you really want to build a full-scale system that is really aware of this quality of service, you really need to incorporate quality of service in all of those components. Okay, and you know this paper by now, and this is the other paper that I mentioned that looks at that 5,000x latency increase and how to reduce that. Okay, but basically, we somehow need to solve the problem. One solution to the problem is actually you have this 1,000-core system and run one application in it, right? You waste a lot of energy. I don't think that's a good solution. Basically, inter-thread interference is uncontrolled in many resources, memory control, interconnect, and caches. We somehow need to control it. Or design interference-aware or quality of service-aware, I don't know why this is blinking, memory system. So I think there are three major challenges over here. And these are, I think we really need to do all of these. First of all, we want to minimize the inter-thread interference as much as possible to begin with. Right? That's reducing inter-thread interference. This clearly improves system performance and utilization, and it reduces serialization and core starvation. If you can minimize it, that's good. But there are cases where you cannot minimize it clearly. You really have this clash or conflict. Then you need to control it, basically. Then the question is, how do you control it? Right? You need to somehow provide mechanisms to enable both the system software and the hardware to enforce quality of service policies, while of course providing high system performance. You don't want to have the situation where you have 1,000 cores and you're running one application in it. And on top of this, I don't think this is also enough. You really need to make the memory system more configurable and flexible, because there is no single quality of service policy, especially if you're building a general purpose system. There may be many quality of service policies that you want to employ, right? And this depends on the applications that you're running also. So you really want to enable flexible mechanisms that can achieve many goals. Sometimes you want fairness. Sometimes you want some particular thread to be prioritized. Sometimes you want multiple sets of threads to be prioritized. Sometimes you don't care at all, right? because somehow the application is really occupying the cores, and you don't want any fairness policy, right? Because it so happens that it works. So that requires some configurability and flexibility, and that makes the system even more complicated. I think all of these really are required for a quality of service aware memory system. So I'm going to give you some approaches to enable this. And I think fundamentally they break down into two. The first one is making the resources smarter. I call this smart resources. Today the resources are not aware of interference, so why don't we make them aware of this interference and design interference control, reduction, and configurability mechanisms. This leads to quality of service aware memory controllers, interconnects, and caches, and whatever resources that you have. Each resource is designed to be quality of service aware. And this makes sense clearly, right? Quality of service aware SSD, for example, hard disks. In fact, hard disks have some quality of service mechanisms built into them today, maybe not in the level that we desire. Surprisingly, SSDs don't have as much quality of service mechanisms. I think that needs to be rethought also. Okay, the other approach is very different. These are orthogonal approaches, but they can be combined together. Basically, dumb resources. I call this dumb resources, meaning keep the resources similarly to what they are, or maybe optimize the resources for maximal throughput or minimal latency. Don't care about quality of service as much, but somehow handle interference on some other side. Basically, this is the... Okay, let me try to do this one. Basically, control the interference in some other way. For example, by source throttling. I call this is kind of similar to the picture that I showed you earlier. I want to draw it again, but it's not letting me to manage this well. Okay, there it is. Maybe I'll draw it over here. So you have this cloud, let's say. This is really your memory system. But you can really think of this as the internet as well, right? And you have these agents that are injecting stuff into your system. They can be cores, accelerators, or whatever. Okay, I don't want to add more. You get the picture. But basically, this memory system is free for all. There are no quality of service mechanisms inside. But on the boundary, you have throttling mechanisms. So the idea is somehow to monitor what's going on inside by putting some monitoring mechanisms and figuring out, okay, this application really is destroying someone else's performance, so throttle it so that it doesn't inject as much. This is actually employed in the internet, for example. A lot of TCP/IP protocols actually have this sort of congestion control mechanisms. You can think of this as congestion control also. But it's not just congestion, it's also about interference control. Like, if this is causing a lot of interference to this one, throttle this one out. So that's a separate approach, clearly. The resources are dumb, they're not aware of the interference, but you somehow collect some metrics to figure out which one is destroying which other. Does that make sense? And this is also a very important approach, I think. Clearly, the other approach is partitioning, data mapping to memory controllers. And if I have to demonstrate it with this one, I have to erase it. Do you see an eraser? I see an eraser, but not specialized for some other function. I guess we don't have an eraser specialized for this function, so I'm going to do it over here. But basically, partitioning is this, right? Okay, maybe if I start with the cloud. Yeah, resources here, resources here, resources here, resources here. They're basically partitioned, right? And this may be a dynamic mapping of agents to different partitions, right? This is like the Zürich airport, if you remember. Clearly, these two agents interfere with each other over here, but if they're not interfering badly with each other, it's okay, right? These two agents interfere with each other, but the different partitions, the agents that are mapped to different partitions don't interfere with each other, right? Clearly, this is data mapping to different memory controllers, falls into this sort of picture. But also, thread schedulings to cores can fall into this picture as well, right? Basically, you may imagine scheduling threads to this partition, right? Such that the threads that are not bad at interfering with each other interfere with each other. But if a thread X interferes really badly with thread Y, you map them to different partitions. That's the idea. So the last two are actually similar in some sense. One is really partitioning in terms of space. The other is really, you can think of it, it's also space, but it's also space and time. But we will see both examples. Okay. And clearly these are fundamentally different from the smart resources, because you may have the resources not so smart in this case, but you can still gain a lot in terms of quality of service and performance isolation. So we'll start with the quality of service over memory controller part, and you're going to implement this in your lab, and you're going to have fun with it. But before we go into, let me go over these different approaches again. Basically, the goal is to really reduce and control inter-thread memory interference, and there are 4 fundamental techniques, I think. If you come up with a 5th one, let me know. Prioritization or request scheduling is one. Data mapping is another one. Core and source throttling, which we showed over here, is another one. And the last one is application and thread scheduling. Let me know if you come up with another one later. Okay, so we're going to focus on this one. And I've shown you this picture before. We're going to make it a bit more complicated. Basically, the job of the memory controller is to resolve memory contention by scheduling requests. And before we were talking about how to schedule requests to maximize system performance. Now we also want fairness to applications and some configurability to system software so that we can decide which application gets more of the resource when needed. So clearly, if you want to do something like this, the memory controller needs to be aware of threads. Right? So basically, the memory controller needs to know which requests are coming from which hardware context. And I don't think this is very hard today, actually. Initially, when we were talking about this, this was, for some reason, a big deal for some hardware designers. Oh, how do we communicate the thread ID to the memory controller? It's not that hard. Just add a field to your memory request. But this also gives you the mindset of the hardware designer, right? They're used to doing some things in some way, and they want to keep doing the thing exactly the same way. So even the thread ID is a huge burden for them, right? I don't think this is a very, very valid excuse as a hardware designer. Don't become a hardware designer like that. If you do it that way, because then there's no progress, right? Just thread ID, send it over. You're already sending over the address, right? Okay. So the next few slides I'm going to skip, but this is for your benefit, basically. This is like the evolution of memory scheduling. We're going to cover some of these things, not all of these things. But if you ever want to learn more about some other things, take a look. Okay, this is fun, right? Okay, so let's start with the first one. So if you remember, memory performance attacks leads to unfair slowdowns. And we wanted to solve that problem initially. I'm going to give you the basic idea of stall time fair memory scheduling. Basically, the goal here is to really balance the slowdowns, right? This is the picture that you get with unfair slowdown. How do you solve this unfairness? And I've already given you the reasons. And the idea is very simple. Fairness is actually a very interesting thing, because fairness, whenever you deal with fairness, it's not like performance, right? Performance you can quantify easily. You can have a metric for it. Execution time, nobody is going to argue that execution time is your performance metric, right? People can say, okay, I don't need this much performance, that's fine. But when you talk about fairness, now you run into the territory of how do you define fairness, right? And that's true for human relations, and that's also true for machines, right? You need to have some sort of definition of fairness, and usually any sort of definition of fairness can be attacked. For example, should the fairness be defined in terms of bandwidth? Each thread gets equal bandwidth. Is that a good definition of fairness? Or if it's a good definition of fairness, under what circumstances is it a good definition of fairness? Let's assume you have bandwidth n, and you're running 4 threads. Each thread gets n divided by 4. Is everyone happy? What do you think? Is that a good definition? Depends on your goal. Depends is the right answer, basically. I don't think it's a good definition in the end from an end-to-end application performance perspective, because who cares about the bandwidth I'm getting, right? As an application designer or a user, I really care about how long it takes to execute this application, right? As long as there's no problem with application performances, I don't really care about the bandwidth. Besides, if you partition the bandwidth hard, like n divided by 4, you run into the problem that we discussed again earlier, right? Some application may need n divided by 2. Some application may need n divided by 16. And basically, you're really wasting some of the bandwidth, and you're not using it for some applications. So basically, we took a cut at the fairness definition also, and we have some fairness definition, which we're going to deconstruct later on also. But basically, this was our goal. If you have these unfair slowdowns, if you want fairness, threads sharing the main memory should experience similar slowdowns compared to when they're run alone. And we call this fair scheduling. And this actually has some nice properties. Basically, it also improves overall system performance by ensuring cores make proportional progress. Basically, they're slowed down proportionally. And it turns out they're designs that are done for operating systems Operating systems actually implicitly assumes proportional progress in general. Whenever they schedule an application to a core, they assume that the application is going to make progress. They're not designed, or maybe they don't care in the end. Basically, they schedule applications to multiple cores, and they're assuming that things make progress. What is really bad is that one application doesn't make progress, and the other one makes a lot of progress. Right? So there's actually some things that need to be done in this case. The operating system today is not aware of the lack of progress an application is making. There's no cycle level accounting that happens. The operating system, when it schedules an application to a core, it assumes that the progress is happening. But as we already very well know that that's not the case, right? If you have some unfairness in the scheduling. So we wanted to change the memory controller such that you get this proportional slowdowns. And the idea, once you have that, is to have the memory controller estimate each thread slowdown due to interference and schedule the request in a way to balance the slowdowns. It sounds easier than done. This is actually very complex. I don't think this is very easy to build, but this was our first cut scheduler. So let's go into a little bit more of this. We call this stall time fairness, and we define the DRAM system to be fair if it equalizes the slowdown of equal priority threads. That's very important, of course. Threads need to be equal priority. Once you introduce high priority threads, that's a very different situation. You don't want to balance the slowdown of a high priority thread with a low priority thread. And the paper discusses how to handle different priority threads. So we define DRAM related stall time as the time a thread spends waiting for DRAM. So we want to really isolate the time that the thread spends waiting for DRAM, because the thread spends some time waiting for other stuff that happens in the core also, right? We cannot do anything about that in the memory scheduler. We're taking a memory scheduler centric perspective here. And then you have two different types of these stall time. One is stall time shared. That's the stall time, DRAM related stall time of the thread when the thread runs with other threads, when it's running together with many other threads in the system. And you also have stall time alone. That's the DRAM related stall time of the thread if the thread is running alone. And the memory slowdown is defined as stall time shared divided by stall time alone. And that's the relative increase in stall time, basically. So for example, if a thread, when it's running alone, it stalls for 1 second for memory. And when it's running together with 4 other threads, it stalls down by 10 seconds. Its slowdown, memory slowdown is 10. Another thread, if it's when it's running alone, it stalls for 1 second. When it's running together with other threads, it stalls for 2 seconds. Its slowdown is 2. Right? And these two threads, baseline is the same, right? 1. Okay. So the stall time fair memory scheduler, its goal is to equalize the memory slowdown metric for interfering threads without sacrificing performance. That's the goal. So there are a bunch of good things about this metric if you read the paper. I'm not going to assign this paper, but if you read the paper, you will see that this considers the inherent DRAM performance of each thread, and it aims to allow proportional progress of the threads. It's better than bandwidth partitioning, I think, in general. Although bandwidth partitioning works in cases where you know the bandwidth demands of the threads. If you actually really know the bandwidth demands of the threads, then that's good, I think. You can use that. But usually you don't know that very well. Okay, so the question is, of course, how do you do this? Clearly, when you're running together with many threads, you can relatively easily get ST shared. But how do you get ST alone, stall time alone? One way is to actually, okay, I'm running together with other threads, so I'm going to kick out all of the other threads and look at my stall time alone. That doesn't sound very good, right? Because that reduces your overall system throughput. That's one way of doing it. It's possible to do it. But it has two issues. One, it reduces your overall system throughput. The second is you're measuring the stall time alone at this phase, but maybe you run into you move into some other phase later on, and you need to measure the stall time alone all the time when you change phases in terms of workload. So basically what we did was we actually added hardware to estimate the stall time alone. So basically for each thread, the DRAM controller tracks stall time shared, estimates stall time alone, and each cycle the DRAM controller computes a slowdown, stall time shared divided by stall time alone, for threads with legal requests. I'm not going to go into the estimation of stall time alone. I'll give you a basic idea very quickly, but the paper has a lot more detail on it. But assuming that you compute the slowdown for threads with legal requests, you can compute an unfairness value, which is the maximum slowdown of any thread divided by minimum slowdown of any thread. And then the scheduling policy is relatively simple. Basically, if unfairness is not bad in the system, what does not bad mean? It's less than some threshold. and that threshold can be supplied by system software. It should be supplied by system software actually. You use a DRAM throughput-oriented scheduling policy, which is FRF-CFS, the baseline overhead first base scheduling policy. Because unfairness is not bad, right? It's under control. But if unfairness is bad, it's greater than some threshold, then you switch to a fairness-oriented scheduling policy, where you prioritize a request from the thread that has been slowed down the max. That's the idea. And this is a prioritization order again. All else being equal, you still do row hit first, and all else being equal, you still do oldest first. This part is really FRF-CFS, but we add another rule over here saying that prioritize the requests from the thread that has been slowed down the most. And this actually helps a lot with the fairness. Let's take a look at this in operation. So now, for now, assume that you're able to estimate ST alone accurately. It turns out this is not very easy. That's why this controller is very hard to build in real life. But this is a very good conceptual exercise to enable research in later memory controllers. So you can guess, for example, how do you estimate stall time alone? For example, whenever you're delayed, so the way we do it actually, very, very high level, we basically try to figure out, you know stall time shared, you know how long a thread is waiting for memory, right? Because whenever you're stalled in the core, because you have a request to memory, you can count the number of cycles, right? That's clearly the number of cycles you're waiting for memory. Some part of that is really needed when you're running alone. Some part of that is not needed. Some part of it's caused because somebody's interfering with you, right? We call this the excess stall time excess. And we reduce the stall time alone estimation problem to the estimation of the stall time excess. Basically, stall time alone equals stall time shared minus some excess stall time, extra stall time that you're waiting because somebody is interfering with you. Then the question is, how do you estimate that excess stall time, extra stall time? And you can actually add some heuristics into your memory controller to estimate it. So for example, you have thread A and thread B. Both of them have requests to the same bank. The memory controller picks thread B. Clearly, thread A is incurring excess latency in this case, right? So you count some number of cycles into the excess stall time. But of course, it's not completely accurate because this may be happening across many banks. So there's some overlapping of this excess stall time. And that's really where the difficulty comes in. How do you actually take into account that overlapping of excess stall time? And that's why this estimation is not completely accurate. But it gives you accurate enough results so that you get better fairness in the system and better performance. Okay, I think I said enough about excess stall time estimation. Good thing I'm not having you build this one in your simulator because it's not going to be fun. Although we will see that this is really good. If you can actually do this perfectly, which is really hard I think, then you can get a very good estimation of the slowdown of a thread when it's running together with other threads, and you can use that for a lot of performance optimizations. So this is a very good thing to strive for. Okay, so let's take a look at STFM in operation. Basically, you compute the slowdowns of each thread compared to when it's running alone. You compute the unfairness, and let's assume that we have an unfairness, tolerable unfairness threshold, 1.05. Basically, the differences between slowdowns cannot exceed 1.05. Let's take a look at the same example where we have the streaming thread, the blue one, and the random access thread. So initially, the streaming thread gets scheduled, nobody gets delayed. But later, when you schedule this request from the streaming thread to row buffer row 0, T1 gets delayed, right? And the memory controller keeps track of that. It increases the slowdown of T1. That's the idea. And unfairness increases. Next cycle, you have a scheduling decision to make. Which one do you pick? Basically, unfairness is under control, and I have a row that's open, and I have a request that's going to that row. Because unfairness is under control, I'm going to pick thread 0. Right? And that's what happens. Now unfairness increases. Clearly, slowdown of this increase because this is getting delayed. Now this becomes higher than the tolerable unfairness threshold. In the next scheduling cycle, you have another choice. And the choice is made in favor of thread 1 because unfairness is not tolerable anymore. And thread 1 is okay, apparently it's not tolerable. Even my computer cannot tolerate it. Okay. And thread 1 is the thread that has been slowed down the max, and the memory scheduler picks that thread. Well, that thread. And clearly this causes some problem in the row buffer. Even though row buffer, there's a request to the same row, you're not picking that. So you cause a row buffer conflict. So you need to take that into account, right? Now thread 0 slows down because the next request is going to the same row, right? Now that reduces unfairness, which is good. And now you pick the oldest one because there's no thread that is to the row that's open. And you pick the oldest one, and that increases unfairness for both of them actually, because this one got a row buffer conflict and this one got delayed beyond this one, right? But this unfairness is still under control, and because of that you exploit row buffer locality, that increases the unfairness, and you get the idea hopefully, right? Basically, you keep switching between this fairness-oriented and throughput-oriented scheduling policy over time. And of course, this unfairness threshold is important. If this is too high, then you never switch to the fairness-oriented. If this is too low, you oscillate quite a bit. So you really want some hysteresis in this one also. And the paper analyzes this unfairness threshold. Yes?
Isn't this exactly the idea in the first paper we were assigned?
That's right, yes. But that one didn't really have a good implementation of it. The first paper was really high level, and this next paper has a very good implementation of it.
Fair mem solution.
Exactly, exactly. So that's good. You read the paper. Yeah. How many other people have read the paper, by the way? Okay, good. But you weren't talking about it. Okay, good. Yeah, it's the same idea. The key difference is how do you actually estimate these? Okay. Okay. Okay, so I'm not going to talk about the results, but it turns out the results are very good. And you're actually going to see another baseline comparison in this paper, but you'll also see that in the emulator implementation that you do. But let's talk about the upsides and downsides of this algorithm. Basically, this is really the first algorithm and implementation for fair multi-core memory scheduling. It provides a mechanism, on top of this, it provides a mechanism to estimate memory slowdown of a thread. I think this is really important, as we will see over here. Basically, it's good at providing fairness, and being fair can also improve performance. You've seen this also in the paper. The downside is it doesn't handle all types of interference. So let me go into a little bit of this more. So if you perfectly estimate this, now you know exactly how much you're slowing down a thread. Now you can actually do a lot of performance optimization. So somebody can actually say, I want my slowdown to be no more than 2x. Right? And you can satisfy that performance guarantee. So later work has improved this estimation. It turns out the estimation that's done in this paper is okay for some type of workloads, but it's not okay for some other types of workloads. For example, if the workloads are compute intensive mostly, if they're very memory intensive, the estimation is okay. If they're not, if they're compute intensive, then you have a huge error in the slowdown estimation. And there's some later work that's actually made it much better. So today, with some other mechanisms that we may talk about, you can estimate the slowdown of a thread within 10% error. 10% is not bad, I think. Under some conditions, of course. But I think there needs to be more mechanisms to do this estimation more accurately. So the downsides, of course, it doesn't handle all types of interference. I'll give you an example in a little bit. It's somewhat complex to implement. I would remove this somewhat, actually. It's complex to implement, basically. It's not easy to implement this. And slowdown estimations can be incorrect, actually. But I would encourage you to take a look at this. Now let's take a look at a very different approach. So we don't want to estimate slowdowns in this case, but we want to exploit some of the insights. And we're going to exploit some other insights over here as well. By the way, any questions? Okay. So this paper actually tackles multiple things. And I'm going to give you one of the important things over here. And we already know that processors tolerate latency of memory requests by generating multiple outstanding requests, right? You try to overlap the latencies of multiple requests. This is called memory level parallelism. Out-of-order execution generates those requests. Non-blocking caches, run-ahead execution. They all try to parallelize requests. Right? Now, this is all good. But these are effective only if the memory controller actually services the multiple requests in parallel in the different DRAM banks. Right? If the DRAM controller serializes them, that's not good. And I'm going to give you a pictorial example. In existing systems, multiple threads share the DRAM controller, and because DRAM controllers are not aware of a thread's memory level parallelism, they can service each thread's outstanding request serially and not in parallel. And this can destroy the effectiveness of all of these techniques that people work hard to develop. So let's take a look at an example. Let's assume that you're running a single thread and you have two banks only. The thread computes and it generates two DRAM requests to different banks. Bank 0, bank 1. Ignore the rows, it doesn't matter in this example. Basically, it sends it to the memory controller consecutively sends the requests to different banks, and in the meantime, thread starts stalling, clearly, right? And it stalls until the requests come back. Assume that you need both of the requests to make progress. The thread stalls until both of the requests are done, and then it can compute. Now, this is nice. Even though there were two requests, the latency of both of those requests overlapped mostly. As a result, you didn't stall two times. You stalled only once, approximately, for two requests. That's the idea. Bank access latency of the two requests are overlapped. Now, let's take a look at another example where you're running two of the same threads for simplicity. A and B, both of the threads compute. They both hit two DRAM requests, and the DRAM requests come to DRAM in this order, let's say. And the memory scheduler goes through the request in this order. It takes thread A's request to bank 0, schedules it. Both threads stall clearly. It takes thread B's request to bank 1 and schedules it. Now both threads keep stalling. And then this is done. It's sent back to the core, but this thread cannot continue because it's still needing this one, right? The second request. And the memory controller picks this request and schedules to bank 0. And then both threads keep stalling again. This thread's request is done, but this thread now cannot continue because it's still waiting for this one to complete. Now the memory controller schedules it to bank 1 because bank 1 becomes free. Now both threads stall because it turns out both of them have requests waiting in the banks. Right? They're being serviced in the banks. And then eventually bank 0 finishes servicing thread B's second request, and bank 1 finishes servicing thread A's second request, and both threads can continue computation. Right? So let's take a look at what happened over here. Because of the way we scheduled the requests in the memory controller, both threads' requests are serialized. Right? And as a result, each thread stalls for approximately 2 bank access latencies. So they didn't overlap any of the latencies. Well, maybe there was a little overlapping here, right? So this sounds bad. The key question is, can we do better, right? And the idea is yes, basically. The answer is yes. So how can you do better? You need to realize that you can overlap at least one thread's requests, right? And that's the idea over here. Same scenario. This is the baseline schedule that I showed you. A parallelism-aware schedule would do something different. Parallelism meaning memory level parallelism or bank level parallelism. Both threads compute. They both generate the same request in the same order. And the memory controller takes the first thread's request to bank 0 and schedules it. And both threads stall clearly. Now the memory controller is parallelism aware. It says, oh, I've scheduled thread A's request to bank 0. Bank 1 is idle, and bank 1 has 2 requests contending for it, thread B's request and thread A's request. If I take thread A's request and schedule it, thread A's request will be parallelized. So I'm going to take thread A's requests, because I don't want to serialize thread A's requests. That's the idea over here. And if you do that, now thread A, both threads stall clearly, but thread A's requests make progress. Thread B's requests are not making any progress over here clearly. Now bank 0 gets done. Thread B's request to bank 0 gets scheduled. Bank 1 gets done. Thread B's request to bank 1 gets scheduled. Now what happened is thread A's requests are done, so thread A can continue computation. Right? Thread B is still stalling, and thread B's requests, when thread B's requests are done, thread B can continue computation. That didn't really lose anything. It didn't lose anything. You just reordered the request to maximize the parallelism of thread A. So thread A is going much faster, whereas thread B didn't lose anything. So it sounds like an overall win in terms of system throughput, right? And that's the idea over here. The average stall time is now 1.5 bank access latencies as opposed to 2 bank access latencies. So that's what a parallelism-aware scheduler would do. Does that make sense? This is, of course, a simple example. More complicated examples are coming, and even more complicated examples are in the paper. Okay, so how do you actually enable this? How do you implement something like this? This is simpler to implement clearly than estimating slowdowns, but how do you actually make it even simpler? So there are 2 principles basically. One is parallelism awareness. I've already given this to you. Basically, this dictates that you want to schedule requests from a thread to different banks back to back. And the goal is to preserve each thread's bank level parallelism. But of course, if you keep doing this, this can cause starvation, right? Why? Because you keep scheduling thread A's requests back to back. Thread A makes progress. It generates more requests. And it keeps getting prioritized. And you could cause starvation to other threads. clearly short-term starvation, but it could also be long-term depending on the access patterns that you get. And if you have many, many threads, it could actually be very long-term. Of course, so we want to prevent the starvation. To be able to prevent the starvation, we add another constraint called request batching, another principle. And the idea of request batching is very simple. You group a fixed number of oldest requests from each thread into what is called a batch. And the memory controller treats this batch and prioritizes that batch over all other requests. And it forms a new batch when the current one is done. That's the idea. And this actually eliminates starvation. It provides fairness. So clearly, this is an idea you can employ independently of this one. Actually, both of these ideas you can employ independently of each other, but it turns out they're better when employed together. Because now you have a batching batch. Within the batch, you can do anything you want, clearly. You can allow parallelism awareness. You can exploit this principle because starvation is prevented with the batches. Right? That's the idea. Actually, batching is not a new idea. Batching is done in hard disks, for example. Hard disks get a lot of requests, and they batch them. And the reason they batch them is they have streaming accesses that are consecutive to different blocks in the hard disk, and they also have random accesses. And they form a batch, and they finish that batch before they move to the other batch. What they want to really prevent is a thread that's streaming to keep destroying the performance of another thread that's random access. We will see this later on in memory controllers also. So here we want to do the batching so that we actually eliminate starvation in a similar manner. So let me give you a pictorial example of this. Let's assume we have 2 banks and now 4 different threads. They're kind of equal. Each of them have 2 requests in this case. Let's assume that they're delayed. They're queued here for some reason. You form a batch. And now within the batch, you pick, let's say, thread 0's requests and prioritize them, service them back to back. New requests arrive, but you don't include them in the batch. Otherwise, you may cause starvation. Now, you first finish the batch. T1's requests are prioritized and serviced in parallel. And then T2's requests are prioritized and serviced in parallel, but you don't take T2's requests that are outside the batch. And then you take T3's requests and service them in parallel, and then you form a new batch. And that's how the memory controller keeps operating. Makes sense, hopefully. And it turns out, basically, there are 2 components. You need to batch the requests, and you need to do within batch scheduling. Let's take a look at batching. Batching is actually very, very simple. Each memory request has a bit that's called marked bit, or batch prioritized batch bit associated with it. When you form a batch, you mark up to some number of oldest requests per bank for each thread. So let's say it's marking cap. This is actually a very important parameter that the paper analyzes. These marked requests constitute the batch, and you form a new batch when there are no marked requests are left. Right. That makes sense. And if there are no marked requests to a bank, that's okay. You can serve not marked requests. Basically, this is a prioritization policy. Remember, all memory scheduling policies are better if they're prioritization policies. Marked requests are prioritized over unmarked ones. There's no reordering of requests across batches. And this is what gives you strong guarantees in terms of no starvation. And also it helps fairness. Starvation is clearly guaranteed by batching. Fairness is not guaranteed because fairness is a different definition, right? Starvation is no request starves. If you operate using batches, no request starves. You can guarantee that easily. Fairness is helped by batching, empirically. Of course, the key question is how do you prioritize a request within a batch now? Let's take a look at that. So clearly, within a batch, you can employ any existing DRAM scheduling policy. First ready, first come, first serve exploits row buffer locality, which is good. But we also want to preserve each thread's intra-thread bank level parallelism. So for this, we need to service each thread's request back to back. It turns out these are at odds with each other. Row buffer locality and parallelism are usually at odds with each other. So we want to find a good policy that tries to exploit both. And the idea in this paper that's introduced is to introduce a ranking of threads when the batch is formed. When you form a batch, you also form a ranking of threads, and higher ranked threads are prioritized over lower ranked ones. So why is this ranking good? Basically, if you rank the threads, it improves the likelihood that requests from a thread are serviced in parallel by different banks. So you first take the requests of the highest ranked threads and schedule them. And that thread exploits the parallelism of the banks maximally. And then you take the next highest ranked thread. That thread exploits the parallelism. And then the next highest, right? Clearly the parallelism of the lowest ranked thread will be destroyed if you have a lot of threads. So ranking is important. So different threads are prioritized in the same order across all of the banks. That's why ranking enables you to exploit parallelism. So of course the key question is, how do you compute this ranking? Let me give you the example of ranking first. These are two banks, and you can see the red thread and the blue thread. Assume that the banks are operating independently. They will basically destroy the parallelism of each thread. That's what you see over here. This is what we've also seen earlier, right, in a sense. Basically both of the threads wait. But if you actually rank the thread somehow, based on some metric, thread A is ranked higher than thread B, and both of the banks obey that ranking, this is what you do, right? And this leads to a memory service timeline that looks like this, and thread A waits less. It's exactly the same picture that I showed you, pictorialized in a different way. So it's really about ranking over here. Of course, how do you do that ranking? It turns out this ranking scheme affects both throughput and fairness. Ideally, you want to maximize system throughput and minimize unfairness at the same time. And still, we're using the definition of equalizing the slowdown of all threads in terms of unfairness. So how do you actually do this? Basically, if you want to, from the memory controller's perspective, if you want to maximize system throughput, you really want to minimize the stall time of the threads within the batch, right? Average stall time. That's from the memory controller's perspective. If you want to minimize unfairness, meaning equalize the slowdown of the threads, you really want to service threads with inherently low stall time early in the batch. Right? Now, what does this mean? So assume that you have two threads. One has a stall time of 1 second, the other has a stall time of 10 seconds. Assume that both of them are delayed by 1 second. Who slows down more? Clearly the thread that has the lowest stall time, right? The thread that has the stall time inherently low stall time, the baseline stall time of 1 second slows down by 2x. The thread that has an inherent stall time of 10 seconds slows down by 10%. And if your goal is to equalize the slowdown of threads, you clearly want to prioritize the one that has the lower stall time to begin with. That's the idea over here. It turns out these two things are compatible with each other with this sort of ranking. Shortest stall time first ranking is shortest job first ranking. People actually looked at this quite a bit in factory production, for example. They proved that if you have a single server, this provides optimal system throughput. In this case, we don't have a single server because we have many banks at the same time. It's very difficult to prove things if you have many banks plus row buffers. We actually tried to prove things related to this, but it's not very easy. Locality really destroys a lot of your proofs. But at least we can get that insight. Basically, if you prioritize the jobs that are shorter or that have shorter stall times and rank the jobs that way, jobs are in this case threads that are inside the batch, you can get a good balance between system throughput and fairness at the same time. So for this, the controller estimates each thread's stall time within the batch, and it ranks the threads with the shorter stall time higher. So let's take a look at an example of this. I think this is best understood with an example. We're going to define two things. So we're going to try to do this, shortest stall time first ranking. We have a maximum number of mark requests to any bank. Let's call that the max bank load. That's going to determine the stall time of the thread. Because a thread is limited by the bank that caused the longest stall time for it, right? Assuming its latencies on other banks are overlapped with that bank. We're going to rank the thread with a lower max bank load higher, at least the low stall time. That's the estimation. We also are going to keep track of another value called total number of mark requests, total load, and we're going to use this to break ties, and this will become more clear. We want to rank the thread with lower total load higher. These are threads that are less intensive compared to others. So we're going to look at an example over here. We're going to assume no row buffer. Row buffer actually complicates things a little bit, and the paper has an example with the row buffer, but it's easier to understand without the row buffer over here. Assume everything is a row conflict, basically. And these are requests from different threads to 4 banks. And clearly now threads are uneven. They're heterogeneous, right? Let's compute these values for all of these different threads. Let's take a look at thread 0. Thread 0 is the red one over here. And its max bank load is 1 because the maximum number of requests it has to any bank is 1. And its total load is 3 because it has 3 total requests. So now you got the idea, hopefully. Thread 1, you do the same thing. Isolate its request. Its maximum load to any bank is 2. And it has a total load of 4 requests. Let's take a look at thread 2. Isolate the request of thread 2. Its max bank load is actually 2. It has actually 2 requests to 2 of these banks. But its total load is higher than thread 1, 6. And thread 3 tends to be the most intensive. Its max bank load is 5. The the bank that has the most requests from this thread is this bank, and it has 5 requests, and its total load is 9. Okay? And this is the order in which we receive the requests. And now we can form our ranking, right? We can say thread 0 is the highest ranked thread because it has the smallest maximum number of mark requests to any bank. Thread 1 is higher ranked than thread 2, even though they have the same number of max bank load. Thread 2 happens to be more intensive, and thread 3 is the lowest ranked thread, as you can see over here. Now we're going to use these decisions. So this is our baseline scheduling order. Assume that that's our arrival order, because we're ignoring the row buffer. We're just doing first come, first serve over here. Let's take a look at how much each thread stalls. And I'm going to assign some time units over here. Clearly I'm ignoring some additional penalties over here, but this gives you a very good first order estimate of how long things will take. We're going to compute the stall times of thread 0, thread 1, thread 2, and thread 3. And this is very easy. If I give you this picture, and if I tell you that this is the baseline scheduling order, and banks operate in parallel, if you want to compute the stall time of thread 0, you just look at when is the last time thread 0's request is serviced. When is the time the last request of thread 0 serviced? And you'll find out that it's 4, right? Basically, stall time of thread 0 within this batch is 4. Thread 1, you do the same thing. The last request of thread 1 is serviced after time 4. Thread 2, you do the same thing. The last request is serviced after time 5. And thread 3, you do the same thing. The last request of thread 3 is serviced after time 7. So you get a pretty high stall time. If you average all of those, and that correlates with your progress throughput, you get 5 bank access latencies. Now, parallelism-aware batch scheduling order will do better, because we rank the threads, right? So we rank thread 0 over thread 1, thread 2 over thread 3. We're not going to follow this order. Now we're going to take thread 0's request first and prioritize them. Now if you do that, this is what you get. Thread 0's requests are serviced in parallel across all 3 banks. The last time the latest request of thread 0 is serviced is time 1. So it stalls for 1 time unit. Right? Make sense? Clearly I'm ignoring all of the delays that happen on the bus, right? I'm assuming that the banks are completely in parallel. This gives you a good first order. So thread 0's parallelism is completely preserved, as you can see over here. Thread 1 is the second ranked one. Clearly in the first time unit, you kind of fill, this is like playing Tetris, right? You kind of fill the holes. It's also bin packing. You're really packing bins. You can think of scheduling as bin packing, as you can see. But basically in this first time unit, thread 1's request is scheduled over here because there is no request from thread 0 to bank 0. So thread 1 fills the hole. And thread 1's requests are serviced mostly in parallel in the second time unit. And as a result, thread 2 stalls for only 2 time units. Thread 2 is the highest priority next, and thread 2 looks kind of like this. And the last request of thread 2 is serviced after 4 time units. And thread 3 is the unlucky one, as you can see. We've constructed a nice example over here so that it doesn't get delayed more than this side over here. That's the idea. If you don't have a row buffer conflicts, actually, this is good. If you don't have a row buffer hits, this is good. So you can see that we reduced the stall time significantly for thread 0 and thread 1, and a little bit for thread 2, and we didn't impact the performance of thread 3 within this batch. So this is a local view. There are other requests that may be coming outside this batch clearly, right? So life is not as nice. But within this batch, we've improved performance, if you measure performance in terms of average bank access latency, by 30%. Does that make sense? So that's the beauty of scheduling in a parallelism-aware manner. Okay. So this is a scheduling policy that you come up with in the end. This is PowerBS scheduling policy. Actually, there are multiple variants of it in the paper you will see. The first one, mark requests are prioritized over others. That's the batching component. And the other part is parallelism-aware within batch scheduling. And there's a debate as to which one should be first. Right? Should you prioritize row buffer hits over higher ranked threads? Clearly, higher ranked thread first is the shortest stall time first ranking. But there's also row buffer locality. And these are at odds with each other, as I said, right? The paper looks at reordering this, making higher ranked thread first the higher priority and row hit request first the lower priority. It turns out there's very little difference between them. and all this first has to be at the bottom over here. So there are three properties of this. First of all, actually maybe there are more than three properties, but three major properties. First of all, it exploits both robot for locality and intra-thread bank parallelism, these two things over here. It's work conserving. Basically, this is a prioritization order. Work conserving means that if you have available bandwidth, you're going to use that. Right. In this case, if we have a bank that doesn't have a mark request, we schedule that request. Basically, there's no reason to delay that request, right? Because you're not really delaying anything. That's not exactly true if you take into account the bus, of course. You're delaying something a little bit, but we're going to assume that we're not going to waste the bank bandwidth for this. And the last one is marking cap is important. This is actually important because this determines how big is your batch. How many requests from a thread do you allow into the batch? If you have too small of a cap, you allow very few requests from a thread into a batch, which means that your exploitation of robot for locality will be very low, because you may have a thread that has very good robot for locality, but you're not allowing its request into the batch. If you have too large of a cap, you're allowing a lot of requests from each thread into the batch, and now what's happening is there are some memory non-intensive threads that may inject a request, and they get delayed after a lot of these requests that are already in the batch. So there's this dangerous trade-offs, and this trade-off is analyzed in the paper, and we tried to overcome this trade-off a lot, and we couldn't. If you read the paper, you will see that, you will see our attempts over here. That's why I think human design policies are very difficult to optimize a lot. I believe a machine learning policy will do better than us over here. Okay, so let me give you some results of this. So first of all, this is actually a lot simpler to implement than stall time fair memory scheduling. There are no complex operations, no divisions. It's not on the critical path. The scheduler makes a decision only every DRAM cycle, and this is relatively easy to implement. But later, actually, you will implement a scheduler called Atlas and Bliss. They're even simpler to implement, but Atlas doesn't provide the same guarantees as this one, but Bliss is actually very good. Okay, so let's take a look at the example performance, and then we're going to conclude the lecture. Basically, this shows you the unfairness average across many workloads. You can see that row hit first policy actually leads to a very high unfairness. First come first serve, no scheduling, reduces that unfairness, but it becomes worse, as you can see, as the number of cores increases. So first come first serve is not a solution. NFQ is network fair queuing. It's basically bandwidth partitioning. It also is not very good. You don't want to partition the bandwidth. STFM is what we discussed earlier. It actually reduces the unfairness significantly, as you can see, but PowerBS actually reduces the unfairness even more. So basically, the overall reduction in unfairness is significant, even compared to STFM, which already reduced the unfairness significantly compared to these prior policies, right? Okay, this also improves performance. This is some sort of speed up metric averaged across many workloads. You can see that the performance improvement is significant over the best previous policy, which is STFM. And you can see that FRFCFS and FCFS do not have very good performance, right? So there are multiple reasons why performance is improving in this case. One is better fairness leads to better core utilization. You're making proportional progress in the core, so you're getting better throughput in terms of different cores. That's one reason. The other is also each core's performance is improving because you're really parallelizing the request. You're really reducing the stall time of the cores because of the way we're prioritizing requests inside the batch. Okay. So let me give you the upsides and downsides, and then we're going to conclude. Basically, this is really the first scheduler to address bank parallelism destruction across multiple threads. It's really interesting because people were designing these out-of-order engines that are generating a lot of requests. And it turns out if your memory scheduler doesn't really respect that, you've done all of this hard work to design your core. You're generating multiple requests to overlap the latencies, but the memory scheduler is not overlapping the latencies. That sounds like a bad design, right? So this sort of coordination is really important, I think, going in the systems. You may be locally optimizing a core, but some decision that you're making in the memory controller can be completely against what you've done in the core. That's why it's always good to have a system level perspective. That's why in general, when you're in a company, don't get focused on just your part of the problem. You may be designing the core, and that may be the most important thing for you. And you may be optimizing it very heavily, but there may be something else out there destroying what you're doing. Right? It's very important to be cognizant of this. I think it's a very good example of that. Basically, there's something else out there in the memory controller very simple policy that's destroying what you're doing. Okay, and you've done a lot to actually make it work. So it's a very simple mechanism compared to STFM, but you will see, you will implement even simpler mechanisms in your lab assignment, and you will appreciate the simplicity of those mechanisms, actually. This is still more complex compared to those mechanisms. Batching provides fairness and starvation freedom, and ranking enables parallelism awareness. So these two key principles are important. The downside is actually, it turns out this doesn't always prioritize the latency sensitive applications. And that's exactly why one of the schedulers that you're going to implement is developed, the Atlas scheduler. It turns out we figured out that being homogeneous in terms of admitting the requests into the batch is not a good idea. Basically, if you have a really latency sensitive application, that should bypass this batching. That's the idea. So you cannot treat everyone the same, basically, because everyone doesn't have the same characteristics. And we tried to solve this problem within the constraints of batching in this paper, and we figured out there's no way we could solve the problem. At least our imagination couldn't take us to that way. And then we developed a more heterogeneous policy that basically distinguishes between latency sensitive and bandwidth sensitive applications. So if you really have a latency sensitive application, let it bypass that batch. That's the idea over here. But we're going to talk about that later on. Any questions? Is this interesting? Okay. I really like this area because it's really a very algorithmic approach to memory controller design. Later, there are implementations of it. When you're going to read the Bliss paper actually implemented a lot of this in Verilog and tried to make it high performance. It turns out, even though this is simple, this is not simple enough. If you really want, it could be optimized. I think Bliss paper could have done a better job to optimize it. I think, but I think it's always good to strive for even simpler policies. Okay, if there are no questions, this is a good time to part. I guess I'll see you tomorrow for the review session.